All right, let's jump right in. For decades, we've been on this incredible quest to build machines that can think. But here's the really fascinating part. This journey into the heart of artificial intelligence isn't just about technology. Nope, it's become one of the most powerful tools we have for understanding ourselves. It's like one source says here, the journey into the heart of the machine is ultimately a journey back to ourselves. Every single time we try to teach a machine to see or to learn or to reason, we're forced to look in the mirror and confront the absolute mystery of how we do it ourselves. And this is the question that really frames everything we're going to talk about. We're trying to build a thinking machine, right? But what does it even mean for us to think? Before we can copy intelligence, we have to figure out what it is. And that forces us to look inward. So today, let's explore what AI is actually teaching us about our own amazing brains. To get started, let's unpack this central idea for this whole explainer. It's a concept called the algorithmic mirror. Think of it like this. When we program an AI, we're basically writing down our best guess for how thinking works. The AI then becomes a mirror. It shows us where we got things right, sure, but way more importantly, it shows us where our own understanding is totally incomplete. It literally reflects our own biases, our mental shortcuts, and all our cognitive blind spots. And what this creates is this incredible virtuous cycle. You see, neuroscience inspires AI. Discoveries about, say, our visual cortex gave us the blueprint for things like convolutional neural networks, which are the AIs that are great at seeing images. But then it goes the other way. Those same AI models become these super powerful tools that help neuroscientists make sense of the mountains of data from brain scans. It's this amazing feedback loop, and it's speeding up our understanding of both fields like crazy. And that very feedback loop has forced us to go back and really question our most basic metaphor for the mind. For the better part of a century, we've had one main idea about what the brain actually is. Yeah, ever since computers first came on the scene, we've been describing our own minds using computer language. We talk about storage, processing, algorithms, buffers. This idea, the information processing metaphor, it was super useful for a long, long time. But now, as we build these incredibly powerful AIs, the cracks in that analogy are really starting to show. The source material breaks down the kind of faulty logic we've been stuck on. It goes like this. We see computers doing intelligent things. We know computers are information processors. So we make this giant logical leap and conclude that anything that's intelligent, including us, must be an information processor in the exact same way. But you know what? That's a huge assumption, and it might just be wrong. And we can actually prove that this is a mismatch with some pretty jaw-dropping numbers. Let's start here. How much data, how much raw information do you think is in a lifetime of experiences? All the sights, the sounds, the feelings, over, say, 100 years. Get ready for this. The answer, based on a pretty conservative calculation, is just under 9.5 quadrillion bits. A quadrillion. That is a staggering, almost unimaginable amount of information that your brain would need to store if it worked like a digital hard drive. Okay, so that's what we'd need to store. Now for the really crucial follow-up question, what's the absolute best case, most optimistic estimate for the brain's actual physical storage capacity based on all its synapses? It's about 2.8 quadrillion bits. And right there, you see the problem, don't you? Even being super generous, the brain's physical hard drive space is less than a third of what it would need to store a lifetime of memories, the way a computer does. The bottom line is the numbers just don't add up. This isn't some philosophical debate anymore, it's a mathematical reality. The brain simply cannot be a digital computer in the way we think of one. It has to be running on a completely different and, frankly, a far more elegant and efficient operating system. So that math problem forces us to look even closer. Let's do a direct comparison between the architecture of AI and the brain. I'm talking silicon versus our biological wetware. This is where the differences just get wild. Now this, to me, is the most mind-blowing comparison of all. The human brain works its magic on about 20 watts of power. That's a dim light bulb. Meanwhile, training and running a big AI model can take megawatts of power. That's 1,000,000 times more energy. It's just an incredible testament to the insane efficiency of evolution. And then there's how we learn. A human, even a child, can often see something just one time, a new type of dog, a new person's face, and remember it forever. We call that one-shot learning. AI, on the other hand, usually needs to see millions of examples from gigantic datasets just to learn the same basic concept. It's a completely different game. Okay, this table really gets into the nitty-gritty. Our brain's architecture is massively parallel. Everything is happening at once, and memory and processing are all tangled up together. AI is mostly built on what's called the von Neumann architecture, with a separate CPU and memory, which creates a data bottleneck. And our memory? It's associative, it changes, it's reconstructive. And AI's memory is a perfect digital copy. It's flawless, but it's static. You see, these aren't just different versions of the same thing. They are fundamentally different solutions to the problem of intelligence. So if AI is so radically different from us, what do its unique struggles and its weird successes actually tell us about our own minds? Well, this is where we get some really profound insights. It all starts with something called Moravec's paradox. And the basic idea is this. The things we think of as the pinnacles of human intelligence, playing chess at a grandmaster level or doing complex calculus, are actually pretty easy for computers. But the stuff a toddler can do without even thinking, that stuff is unbelievably difficult for an AI. So, playing chess like a world champion? A piece of cake for AI. But understanding the subtle social cues in a simple conversation? Immensely hard. This paradox teaches us something so critical about ourselves. Our so-called effortless skills, like perception, moving around, just basic common sense, these are actually our greatest computational achievements, fine-tuned over hundreds of millions of years of evolution. This also completely reframes how we should think about our own memory. An AI's memory is like a perfect digital file in a cabinet. You pull it out, it's exactly the same every time. But human memory, it's not like that at all. It's a dynamic, creative act. Every time you remember something, you're not just pulling up a file. You are actively reconstructing a story. And you often change it a little bit every single time you tell it. And all of this, it brings us to some really big, really important questions about our own future, especially as we keep building machines that get more and more intelligent. Interacting with AI is a total double-edged sword. On one hand, there's a real risk of what's called cognitive offloading, just letting the machines do our thinking for us, which could make our own critical thinking skills weaker. But on the other hand, there's this incredible reward. AI is a mirror that lets us study human psychology and consciousness on a scale we've never seen before. The challenge for all of us is to find that balance, to use these tools to make our own intelligence better, not just to replace it. So in the end, we're left with this massive, profound question. If we actually succeed, if we build machines that can solve all our practical problems, from curing diseases to managing resources, what then becomes the purpose of the human mind? The quest to build AI might force us not just to understand our own intelligence, but to decide what we want it to be for. And that's a question we're all going to have to answer together.